In this chapter, we'll discuss different types of algebraic systems, model the algebraic equations, and simulate them in Simulink. Then we'll create a subsystem, run static checks, and define test cases to verify our unit designs dynamically. We will also discover lookup tables. And we will discuss how to avoid algebraic loops in numerical simulations. Here is the overall model that we will develop in this course. The algebraic system will be needed to convert state values from the centigrade to the Fahrenheit scale. You will not need any reference files for exercises, as we will build all the models from scratch, test them, and then integrate them. The most prominent algebraic equations are linear and quadratic, and below you see the general form of an algebraic equation. We'll model a linear equation. In a linear equation, each term is either a constant or the product of constant and a single input variable. Linear equations describe a relationship between two lines on the plane, like the red and the blue line. This linear equations describe the relationships between the temperature on the Fahrenheit and on the Celsius scales. We'll first use the mathematical expressions to model the equations in Simulink. And after it, we'll model the same behavior with a lookup table. We will compare the computed simulation results and discuss their numeric differences and acceptable tolerance values. Simulink Library Browser provides the Simulink blocks we need for modeling systems in Simulink. You can start the Simulink Library Browser in two ways. You can use the Simulink icon in MATLAB or type Simulink in the MATLAB command window. With Simulink Library Browser, you can have access to Simulink blocksets, libraries, and single blocks. You can search in the Simulink Library Browser. And you can open the Simulink editor for graphical block-based design. The smallest unit of the Simulink block diagram is a single block. The block functionality is masked, and each basic block has a graphical mask symbol. When double-clicking on the mask, a parameter dialog will appear. Here you can customize the settings of the block. The mask dialog includes block type, description, parameter dialog, and help. Let us create our first Simulink model where we convert temperature values in centigrade to temperature values in Fahrenheit. We will implement the formula by adding, connecting, and calibrating the Simulink blocks from the Simulink Library Browser. As system design gets more and more complex, it would be impossible to keep all the functionality in one single hierarchy. Simulink provides a mechanism for creation of hierarchical modules using subsystems. To create a module in Simulink, select all elements of the diagram which belong to one module, go to the context menu with right mouse click and click on Create Subsystem. And now you can rename the subsystem and the interfaces for better documentation. The subsystem can be simulated and tested in Simulink. For this, we need a test harness with input and parameter values, as well as reference output values to be compared with real outputs of the subsystem. Simulink Sources Library includes many input signal generators for this purpose. We will use a ramp block to generate the input, and we will use Simulink viewers to view the outputs. In our second example, we will use an alternative way of implementing a linear equation. We'll use the lookup table. Here in this Simulink model, we will convert the temperature values in Fahrenheit to the temperature values in centigrade. Instead of implementing the linear equations, this time, we will map the lines, inputs to outputs, with a 1D lookup table block from the Simulink Library Browser. Such mapping of a red line to the blue line can be done in the block dialog. The mapping function will include the breakpoints of the red line. This is our input. And we map it to the blue line, and this is something that we look up in the table. And this is our output. So all these things can be defined in the mask dialog of the lookup table. Algebraic loops are common in algebraic equations. One example is the equation in which the output equals the input minus output. Mathematically, this loop implies that the output of the sum block is an algebraic variable that is constrained the first input minus itself. It is an algebraic loop. The solution of this simple loop is input over 2. But algebraic loops are difficult to resolve by using pure numerical methods in Simulink, and Simulink throws a warning. In some cases, Simulink can resolve such algebraic loops, but the simulation slows down. We suggest resolving the algebraic loops as a solution for the simple problems. In this case, the optimal solution is the input over 2. In more difficult situations, you will not be able to resolve the algebraic loops. You can break up the algebraic loop by inserting a unit delay block to provide an initial value for the equation. We'll talk about discrete systems later, and we will talk about the unit delay block a lot. But for now, just remember that there are simple ways of resolving the algebraic loops. The best way to do it is finding a solution of the equation. The second best is to use the unit delay. And it works always. But it requires extra memory and extra runtime. In this chapter, we discussed different types of algebraic systems, modeled the algebraic equations, and simulated them in Simulink. We created a subsystem, run static checks, and verified our unit dynamically. We also discovered lookup tables and discussed how to avoid algebraic loops in numerical simulations.